touch this thing. I'll glue those together. Well, I probably won't glue them together. I'll just do part 1, part 2, part 3 is what we'll have. Okay, so questions about that? And then, let me just close this. When might we need a base greater than 16? Well, when memory gets bigger, when hard drive space gets bigger. I mean, we already see it with IP addresses. So let's connect this to networking a little bit for this class. So did any of you use networking as an example in your paper? IPv4 versus IPv6? So our modern day networking thing, so like this computer right here, my IP address in this machine is 172.31.224.12. That's the IP address that I am receiving from the wireless network here on campus. Okay? Now, this address, these numbers are in the range of 0 to 255. And then there's a dot between them. So we have 4 different numbers, each ranging between 0 and 255. So that is an unsigned 8-bit number, correct? Which means the entire IP address is what? It's a 32-bit number. 32 bits make up, total footprint, make up an IP address. It's 32 bits. Well, this used to seem like it was fine. How many computers are on the internet today? That's the technical exact answer is a lot, right? Okay, so given that, we're actually running out of IP addresses. The reason for that is the way IP addresses used to be handed out. Somebody has to be in control of all IP addresses. And you'll learn about this in the networking class, okay, the more details of it. But somebody has to be in charge of all these IP addresses. So when you have a school like Concordia, they ask for an allotment of a certain classification of IP addresses. So let's say we need 5,000 IP addresses. Well, because of our need, we might say, okay, well, we need a C-class IP address allotment. So they might give us 12,000 IP addresses. We only need 5,000. Well, this is all we can give you. We can only subdivide these addresses by, so one place might be 172.blah.blah.blah. So the lowest common denominator is we can give a place 256 unique addresses. After that, we can give them those 256 unique addresses, and then we can hand them either a single 1 or a 2 or a 3 or a 4 from the next digit over. We have to keep giving them those banks. Well, as you keep growing, we have all these wasted IP addresses. Because you have a place like Concordia that has a foothold on, let's say, 12,000 addresses, yet we're using 5,000 of them. So what did we use to try to fix that? Well, we started using what are called network address translation. So if you go out to Best Buy or something, you buy a wireless router for your house. That wireless router gives you IP addresses to your phone and laptop and stuff in your house. And how many of you have a wireless router at home? Okay, a couple of you. Do you know what your IP addresses are? Don't tell me. Do you know? Okay, I'm gonna make a guess. It's either 10.0.0. something or 192.168.1. something. Second one? Okay. Every one of them will be that. Those are non-routable IP addresses. It's a local network inside your home. I guarantee you the address you're getting when you go home tonight, somebody down the street from you has that exact same address. But what they don't have is your router has a unique address on the internet. Or, in some cases, your router might have a 10.something address or a 192.something address, which means that your house is actually part of the NAT at your cable company or the DSL provider. So if Time Warner is handing you a fake IP address, and then you have a router that's plugged into that that's handing out your internal guy's fake IP addresses, I mean, you're all part of this huge farce. Does that kind of make sense? So that's the strategy we've taken to tie up less IP addresses. This is why when you go and shop for internet, one of your options is to get a static IP address. You pay extra for that. You're saying, hi, I want to pay for a real IP address so that I can actually get to my house. Does that make sense? And that's why a lot of these companies have made tons and tons of money. For instance, how many of you use LogMeIn? Okay. You use LogMeIn? Have you do you use any other, like, control your PC remotely? Well, you have a wireless router at your house too, right? Whether you know the IP address or not, I guarantee one of those two was the answer. Okay, it either gave you 192.168 something or 10.0.0. something. Okay, but you can remote into one of your machines at your house, can't you?
No, I'm remoting into work.
Okay, well, but you could. You could install LogMeIn at your machine at home and it will work just fine. Even though she has an IP address that's shared by thousands and thousands and thousands of other people. How does it do it? Her machine at home has the LogMeIn client on it, which connects up to the LogMeIn server and says, hi, I'm part of her account. Whenever she logs in over here, she doesn't talk to her computer directly. She talks up here, which already has maintained a connection back to her computer down here. Because you can't get to her computer down here because it's not unique. Because there's 4 million other people in the world that have the same phone number as her computer. That make sense? Okay, so all these things have to do with these number systems. So we haven't moved to this yet, but you maybe have seen this before that when you go to set up a network card in a computer, you'll see IPv4 is the default. But you'll see another thing where probably a checkbox that says use IPv6. So that's the next version of IP addresses, which uses 16-bit memory blocks instead of 8-bit memory blocks. So it would be 16-bit by 16-bit by 16-bit by 16-bit. So a 64-bit block of numbers, which can hold much, much, much larger number of unique elements, right? Well, when will we need something bigger than that? Well, when we get even more computers. Early days of the internet, we didn't have computers in our pockets. We had a bunch of modems. Now, most of us have multiple computing devices, right? How many of you have a desktop at home? How many of you have a desktop and a laptop? You have a desktop, a laptop, and a smartphone. And an iPad. And a toaster that knows how to check email. Right? You get what I'm... And our world population does not need to get bigger in order for us to need more IP addresses. We just keep getting more junk, right? So those were all kind of things you could have seen. I didn't necessarily expect you to go that deep into any individual realm. So I kind of tried to give you some information that was probably beyond what you found for your papers or really looked into for your papers. But really, these base systems go pretty deep in terms of the same patterns, but in all sorts of different areas. Okay? All right. So,
I realized that when the program that I made, going from decimal to base, if the base was evenly divisible into the number that you put in, it didn't work. So I'm trying to fix it, and I just messed it up worse.
You messed it up worse.
Yeah, now it's like not giving every. No, it doesn't like it.
All right. Well, wait till you see my solution and tell me if you. Yours might be better than mine. I don't know. We'll see. Okay. Any other questions on this? We're good there? All right, so let's look at homework 4, Unit 2. This guy? All right, write a Java program that has at least the following 2 methods. We should have a static int base to decimal. That takes a method, blah, blah, blah. Okay, so static int base to decimal. I'll just steal this here. I will add in the S. Okay, so we're adding a method called static int base to decimal. And this guy is going to take in a string, which is a number in some base, as well as the base that that number is in, and it should spit out the integer version of that number, correct? The decimal version of that number. So if I were to pass it in the string 101, and say that was in base 2, this guy should give me, this is 1, 2, 4, so this is the number 5, the int 5. Correct? All right, so let's look at the solution for this. So we're going to have something called int place. We're going to start that off at 1. Why is that? Well, let's go to our drawing board here. Draw some pictures. So let's just say that's my binary number, 101. This is the 1's place, the 2's place, the 4's place. Or we can look at it as this is the 2 to the 0's place, 2 to the 1's place, 2 to the 2's place. That makes sense? And what did we do? We multiplied this number by this number and added that to this number times this number and added that to this number times this number. So that is 1 times 1 plus 2 times 0 plus 4 times 1, which is equal to 1 plus 0 plus 4, which is equal to 5. That makes sense? So the way we're going to solve this is I have this guy here as a string. So I have the string representation of 101. And I want to walk this guy from the end to the beginning. Why? Because I need to start my place off at the 1's place. Then it becomes the 2's place. Then it becomes the 4's place. So I'm going to have a variable here named place. And place will start off at the 1's place. No matter what my base is, the first place is always 1. If it's base 2, it's 2 to the 0, which is 1. If it's base 8, it's 8 to the 0, which is 1. If it's base 16, it's 16 to the 0, which is 1. That make sense? All right, so my place will always start off at 1. As I move to the left, as I move from position to position in my string, I'm going to multiply this base, this place, by whatever the base is. So for base 2, it's going to go from a 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. So on and so forth. Okay? So I'm going to go ahead and create an integer called place. Start that guy off at 1. Now I need to walk my string backwards. So I'm going to create my loop. This is my loop pattern that starts at the end of the string and goes towards the beginning of the string. For int I is equal to num dot length, that's the number of characters in num. We're going to say length minus 1 because that's the last legal bucket in num. So if num, in this case, is the string 101, so this guy, if that's what num currently looks like, that guy has a length of 3, legal buckets are 0, 1, 2. So length minus 1 is the last legal bucket. So I'll start I off at the last legal bucket. We're going to keep going as long as I is greater than or equal to 0 because we do want to actually look at the very first bucket, bucket 0. And each time through, we'll subtract 1 from I. All right, so this is our loop pattern for walking a string backwards. And what are we going to do each time? Well, each time we need to take the number value of the character in our string. So for instance, if I say, this is num.char add I, let's just say it's the character 1, I need to turn that into the integer 1. That make sense? So I need to be able to do that. Each digit, excuse me, sorry. I'm going to have a string. We'll do this initially for binary. I'm just going to call it map. I'm going to put in there the legal digits for binary, 0 and 1. So even though this guy's called base to decimal, we're going to solve it for binary to decimal initially. All right. So I'm going to call it, have it 0 and 1. If I'm looking at a char 0, at what position in map is 0 found? Bucket 0. Correct? This is index of. I'm also going to have a sum for my running total to add up all those things. So over here, we have ultimately my sum will be equal to 5. So as I walk through my string, what am I going to do? I'm going to say sum is equal to whatever sum currently is equal to plus map dot index of num dot char at I. So this code right here is going to give me the index of the character that I just pulled out of num. So if this is a binary number and I just pulled out a 0, this will give me the integer 0 because the character 0 is found at bucket 0. If I said give me 1, it'll give me the integer 1 because the character 1 is found at bucket 1 of map. Does that make sense? So we're using index of to solve problems just like we did last time. So I'm going to take that number, I'm going to multiply it by place. And I'll go ahead and put that in parentheses. It's not actually needed, but we'll do it anyways. Order of operation would dictate we should do the multiplication first, but I like to be explicit. All right, so we'll increment sum, and then we need to say place is equal to place times 2 initially. If we're doing this for base 2. Or place equals place times radix. If we're doing this for a generic base. Ultimately, we're returning sum. So if I call this method, and I print out the answer, if I call it passing it 101 and I claim that's base 2, it should give me the number 5. There's my 5. Similarly, if I say 101 in base 10, it'll give me 101. Because 101 in base 10 is equal to 101 in base 10. 101 in base 8 is 65 in base 10. But when we run into problems, actually our code doesn't work for anything bigger than base 2 right now. So it just happened to be that actually it does. It just happened to be I only use zeros and ones in my my question because I only represented zeros and ones here. So if I build this out and say 2, 3, 4, 5, 6, 7, 8, 9, now it'll work for all the bases between 1 and 10. So here's my 137 in 8 is equal to 95 in base 10. Now notice this just kind of goes back to what we were talking about a few minutes ago. It's 135 or whatever I wrote in base 8, but it's only 95 in base 10. Smaller footprint. Okay? Now where we run into problems, so this is almost our complete solution, as long as we don't go above base 10. Where we start running into problems is things like BAD. We're going to try to look for that. We're going to get a bunch of negative ones because it's not going to find it inside of map, and we're going to get a crazy number. Negative 73. Not right. So what we need to do is we need to expand our alphabet. We'll say this is base 16. And there's 2989. So this will work on bases 1 through 36 for base to decimal. Make sense? So questions on that one. So that was the first part of your homework. Okay. Second part of your homework. Decimal to base. This guy right here. This guy's going to take in a number like 2989 and the base we'd like it to become, and we're going to get the string representation of that number. So if I passed in 5 as an int and said I want that in base 2, it should return the string 101 for me. Well, let's look at how that math works. Five divided by 2 is 2. 2 times 2 is 4, with remainder 1. 2 divided by 2 is 1. 1 times 2 is 2, with remainder 0. 1 divided by 2 is 0. 2 goes into 1 0 times. 0 times 2 is 0, with remainder 1. Then we read our answer from bottom up, 101. If I wanted 5 in base 8 instead, do all these divisions by 8 instead of 2. How many times does 8 go into 5? 8 goes into 5 0 times. Sorry, 0 times down here. 0 times 8 is 0, with remainder 5. Oh, 5 in base 8 is the same as 5 in base 10 because they're both in the ones place. So there's my answer, 5. All right, now, the important part to notice here, and I think I gave you a big hint to last class, was that you're done when you hit a 0. When your quotient is a 0, you are done. So let's make this work for binary first. Regardless of what I pass in here, let's just make it work for binary. All right, so I'm going to say while number is greater than 0. Now I'm going to need something to collect my answer in. All right, so I'm going to create a string called answer. We'll start this guy off as the empty string. Okay, now I'm going to actually think about this in terms of the number 6. Base 10 to base 2. Just so the number doesn't read forwards, backwards the same way. For testing purposes. So 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, so we know we're done. 0 times 2 is 0, remainder 1. So the answer here is 110. 110 is the is 6 in base 2. Decimal value 6 in base 2. So we need to actually build our string in reverse. So while number is greater than 0, what will we do? We're going to say answer is equal to the empty string concatenated with number mod 2. For right now, we're going to just assume we're doing this for base 2. Concatenated with answer. Then we're going to say answer is equal to answer divided by 2. Oh, I'm sorry. Number is equal to number divided by 2. And then finally, we will return answer. So to test our decimal or our binary only version of this real quick, we'll come up here. We're going to say driver dot decimal to base. We're going to pass it in 6, and we'll pass it in a 2 even though we're not using radix right now. So 6 comes in for number, 2 comes in for radix, but I hard-coded a 2 in here. And this should give us 110. Now, how do I make that work for any base between 1 and 10? Replace the 2 with radix. So we're going to keep dividing, keep recording the remainder as long as number is greater than 0. As soon as number becomes 0, we're done. Spit out the answer. The one trick here in terms of programming this is we capture the remainder before we do the division. Otherwise, if we do the division first, then try to get the remainder, we've already broken our number because we already divided it before we got the remainder. So the order of operations is important here. We must do this line first before we do this line. All right, so we'll see this still works now that I've just switched up the radix. Similarly, I can say give me the number 643 in base 10, and this should give me 643. Give me the number 413 in base 8. 635. Okay. But where this breaks down is what if I want 2989 in base 16? I get the right answer, but the wrong answer. 11 is a B, 10 is an A, 13 is a D. This is BAD, but I haven't done the mapping. Make sense? So to finish this, I need to actually do my mapping. So I'm going to grab our string map here. We'll duplicate that in decimal to base. And instead of concatenating on number mod radix onto our answer, I'm going to concatenate on map.char at that onto our radix. 0, or map.char at 0 is what? 0. Map.char at 1 is what? Map.char at 2 is what? Map.char at 8 is what? Map.char at 10 is what? So that does the map. So char at is the inverse of index of. So we can use that same trick to go both directions. So now this gives us our BAD. And it still gives us our 6 in binary. 110. That make sense? All right. So those two methods would be reasonable solutions to the homework assignment. And look, it fit all on one screen this time.
So why doesn't the for loop that I made work?
Well, tell me what the... Oh, we're in a second version of this. This was decimal to base, right?
Well,
It was this method?
yeah, right, let me just keep thinking.
Well, you want to tell me what you wrote? And I'll...
No, if it's wrong, I'm embarrassed that I'm wrong about something.
Okay. Go ahead.
How do you know that the base is between 1 and 36 in the first one, the first part of the program?
Up here?
Yeah.
Well, what do you mean, how do I know it's between 1 and 36?
You said that this program will work with any base between 1 and 36, right?
Right.
Yeah. So how do you know that?
26 layers in the alphabet.
Okay.
So here's 26, and then the other 10. 36. Yeah, it just comes, like base 10 is 0 through 9. Those are the legal digits. Base 2, 0 through 1 are legal digits. Base 8, 0 through 7, legal digits. Base 36, 0 through 9, A through Z are the legal digits in base 36. After that, we don't have the alphabet. We're out of characters. There's not a great reason why we couldn't represent base 50. We just can't use the English alphabet to do it. We'd have to use some kind of symbols and stuff like that. Or a larger alphabet. Ugh. All right, what else?
It is the same.
Okay, so let's practice a little more with some of this stuff. So that was your homework assignment. Now yours didn't have to look identical to this. So kind of an interesting thing here. Right here, I have a string, representation of 101. And I've said that's in base 2. And I'm passing it to this function called integer.parseint that takes in a string as the first value, as well as the base that that string's in, and it gives you the decimal version of that. So it gives you base to decimal. It's already written for us in Java. So what can we do here? We can actually replace all of this. With that. So converting between a given base and its decimal is built into Java through a class called integer. Just like the character class lets us do things to chars, integers let us do things with ints. Okay, so if you ever need to do this again, there's a nice shortcut for doing it. All right. Let's do a little more practice here. Let's see. Well, actually, let's introduce arrays, then we'll practice with arrays. We'll do some interesting stuff. Okay, so, well, actually, before we do that, this would be an interesting thing. Let's say that I have a string, hello. And I want to rearrange this string so that it's in alphabetical order. So essentially, I want to sort it. Make sense? So instead of it being hello, I want it to be that alphabetical order. EHLLO. So I want to create a method called sortString. And sortString is going to take in a string that might look like this, and it should spit out a new string that is the original string, but with all the characters rearranged in alphabetical order. How would we pull this off? We got to break this down into baby steps. Am I able to tell if one character comes before another character? What are chars? If you had to tell me everything you could tell me about chars, what would you say? That's it? Nothing? It's a primitive type. What's a primitive type? Okay, built in the language only holds a single value. Okay, so a char is a primitive type. What else? How are chars represented? Since we're talking about data representation. Okay, it's an integer. What kind of integer? Unsigned 16-bit integer. Okay, so it's an unsigned 16-bit integer, so that's 0 to 65,535. How would I compare to see if one char should come before another char? Like, could I ask if A is less than C? Is that an accurate Boolean expression? Is that legal? You shouldn't have to guess. What if I said, is 5 less than 7? Is that legal? Well, why wouldn't this be legal then? You just told me that chars are ints. Is this an int? Is this an int? And this is legal, right? Is this an int? No, not a string. Strings would have double quotes around it, not single quotes. All right, hold on. Let me start this little sequence again. You already told me that chars are ints. This is an int. This is an int. And you've said this is legal, right?
Yeah.
Is this a char? Then is that an int?
Yeah.
Yep. So can I say A less than C? This will be true. A does come before C. So I can compare chars to each other using the primitive comparative operators. Less than, greater than, equal to, not equal to. I can't use ands and ors, but I couldn't use ands and ors on ints either. I can only use those on Boolean expressions. Okay, so I can compare one character to another character to see who comes first. So let's start off by writing a different method. Instead of writing sort string, let's write a method called return smallest char. Return smallest char is going to take a string as a parameter, and it's going to spit out the character, so the char, that is the smallest char in the string. For example, if I passed it the string hello, it should spit out an E. Alphabetically speaking, E comes before all the other characters in that string. That make sense? Okay. How would you do this? In real life, if I handed you a piece of paper and I had the word hello written on it, and I told you to tell me what was the, alphabetically speaking, the first character, the smallest character in hello, you'd say E, right? How did you come to that conclusion? You got to slow yourself down and figure out those baby steps. You somehow compared each individual character, right? Well, you started off, if you're at the very beginning of that string, have you found the smallest character yet? So that's it. H is your current winner, right? H is my current winner. Then you go to the next guy in the string. Should E come before an H? Yep. Got a new winner. Should L come before E? Should L come before E? Should O come before E? We're out of characters. Return our winner. Make sense? So, we're going to need a char, current winner, and just for the sake of this code, let's assume that the string they pass us has at least one character in it. So we'll say this guy is equal to s.char at 0. Then we'll write a little for loop that goes through all of the other characters in S. How would I write that loop? What would be a loop that goes through every single character except the first character? How would you write that loop?
Like, skips the first one, like you showed us last time.
This shouldn't be that difficult anymore. You should be able to do this by now. So I want to look at every character in S, just like we've done before, right? But I want to skip the character at bucket 0. So for int I is equal to not 0, but 1. We'll start off at bucket 1. Keep going as long as I is less than s dot length. Increment I each time. So small modification to our normal spin through every character in our string. Now each time through here, I need to find out if the current guy I'm looking at is a new winner. How do I ask that question? How do I ask, is the next character I'm interested in So if my current winner is H in our little example here, and I'm currently looking at the E, how do I ask, should E come before H? How do I write that code here?
Char. Oh, is it current winner? Wait, I can't see that. Char at I.
Who's char at I?
The H. Or
Who-
the E.
Who owns, it's S. S owns the char at method. So it's S dot char at I. So if you,
Oh, that's what you're asking.
yep, so that character.
Okay.
So the character I in S, what am I going to do with that? So this boils down to, first time through, this will be the char that lives at bucket 1 in S. Second time through would be the char that lives at bucket 2, so on and so forth. What am I going to do with that? I'm asking the question if that character should come before my current winner.
Is less than?
Okay?
S dot char at I plus 1. I don't know. I'm not sure.
I already have current winner right here.
Oh, right.
So I started current winner off at the very first guy, H,
Oh,
in our example.
yeah.
So if that guy is less than current winner, if that's a true statement, if it's true that the current character I'm looking at should come before my current winner, what do I do?
The continue thing? Or return, I guess?
Well, what's this method do? This method figures out what the smallest character in our string is. Right? Well, if I found a guy here that's smaller than current winner, do I know that that guy is the smallest character in the string? We just know he's smaller than the guy I'd already found.
Stored as current winner.
So I need to set current winner equal to S dot char at I. Then it'll spin back up. I will become 1 greater than it used to be. We'll do that comparison again, over and over and over again. And as soon as we get past the end of the for loop, our answer should be in current winner. So if I said system.out.println driver.return smallest char, and I passed it hello, it's going to give me the E. Similarly, if I passed it elephant, it'll give me the A. Make sense? So this little method will go through and it will figure out what the smallest character in a string is.
Oh, wait a second, I have a question.
Okay?
Okay, so if you like capitalize E, then does that make it? It's like a different char.
It is. So what if I say capital A here?
Yeah.
Actually, I got to go the other direction. What if I
So why
say?
give you back capital A?
Because the Unicode value of capital A is smaller than the Unicode value of lowercase a.
Oh.
So let me do E. So it gives me the big E now.
So capitals are.
Capitals are come before the lowercase.
Oh, okay.
So as we have it written right now, it will not pay attention to case. It compares Unicode values, right? Well, what if we want this to look at case? Well, rather than comparing the current winner, I could do it as current winner, but what I need to do is I need to compare them as lowercase. So what I'm going to say is if, or uppercase, I need to compare them as the same case. I could say if the uppercase version of our current character, so there exists, have we looked at the two uppercase method yet?
No.
Okay, so we've looked at the character class, correct? So in that character class, we also have a method called two uppercase. So this is a class method. How do we know? How do we know that two uppercase is a class method? We're seeing it being called here, not defined.
You call it with the class name.
Because we call it with the name of the class. Yep, so we're calling it with a class name. How do we know character is likely a class name?
It's like the Java lang thing.
What do you mean Java lang thing?
It's in the list of things under Java lang.
Well, that's also a true statement. It is in that list, but how do you suspect, just by looking at what you see here, that it is likely a class? It's a naming convention in Java.
It's something dot something.
Even instances would be something dot something. s.char@I. Char@'s an instance method of the string class, because s is an instance of the string class. In Java, naming conventions dictate that classes typically start with a capital letter. Okay, so this is a class method. It takes a char as a parameter. What are we going to do with that char? We're going to convert it to uppercase. So all this crap right here gives me the uppercase version of that char. And I'm going to compare it to the uppercase version of the current winner. Okay, so I could also do lowercase instead of uppercase, but I'm comparing them as the same case. I'm still storing them as whatever case they were originally in, so I'll return the proper case. But I'm always comparing them in uppercase. So now, even though E is a Unicode value, capital E has a Unicode value that's smaller than lowercase a will be returned out of this. Because capital E and capital A is the winner. Make sense? Okay. So that returns smallest. Now we're back to reordering our string. What did I call that method before?
I don't remember. I dare you to call it I don't remember.
Reorder string. So we're back to the method where we want to take a string as a parameter and put that string in alphabetical order. We now have a method that can take in a string and give us the smallest letter. What string would have if I had a string, hello, what letter should come first if I'm putting it in alphabetical order? If I have a string hello, what's the smallest letter in hello? So should the smallest letter go first?
Yeah.
Should. So I can already find out what the first letter is, can't I? Can I find out what the second letter is?
Yeah.
How? What's the second smallest letter in the string?
Skip over the smallest one.
It's the smallest letter after I remove the second smallest. Well, it's the smallest letter after I remove the previous smallest letter.
Yeah.
So now I need to be able to remove a character from a string. So we might write a method. Static string remove first. Well, I don't want to spell that. First char, char C. So I'm going to pass in a character to this guy and a string. So it's going to be called remove first char. We're going to pass it the string. We're going to pass it a char. And this guy should return a new string that is exactly like the original string, but with the very first occurrence of C removed from it. Now remember, strings are not editable. So if we need to take something out of a string, we need to keep everything that is not the first occurrence of C. So I need to build a brand new string. Correct?
Yeah.
String answer starts off as the empty string. Now we need our loop pattern that goes through every character as a string. For int I is equal to 0, I is less than s dot length I plus plus. That's our loop that loops through every single character in a string. Now, I want to keep every single character except the very first occurrence of the character stored in C. And that's important that we make that distinction, because what if I'm looking to remove an E and my word has 4 E's in it? Well, those next 3 E's are probably going to be the next 3 things in line. So I only want to remove one of them from this string. So that means after I skip over the first one, I need to somehow remember that I have skipped over a character, so I've already done my removing. That make sense? How would you do this? Using only what we know how to do so far. Here, I'll ask you this question. What position in S is the first occurrence of C?
Taking an index of.
Using index of.
And then when your I is like for I is less than an index, and then you have stuff, and then once.
Well, we could build a sandwich out of this in a second,
Yeah.
but the point is that initially we know the character that we want to remove. The character we want to remove is s dot index of C. Like you said, it's the index of. So we know that we need to get everything up to, but not including the index of. So we'll start at 0, keep going until we get to s dot index of C, I plus plus. And we want to say less than that index, because we don't want to capture that one. And we'll say answer is equal to answer concatenated with s dot char at I. Okay? So this will get everything on our string up to, but not including, the first occurrence of C. Then we'll write a second loop for int I is equal to s dot index of C plus 1, skip over it. I is less than s dot length I plus plus. Answer is equal to answer concatenated with s dot char at I. finally remove return answer. So let's test this on our elephant. So I'll say driver dot remove first char, passing it elephant, and we'll pass it the lowercase a. So we should get elephant with the a removed. Make sense? Now, what if I said we were not allowed to use the index of method in that particular solution for no good reason other than just practice? So we have to write this method a second time. Call it remove first char 2. Takes a string s and a char c as a parameter. And now we have to come up with an alternate solution. A solution that solves the exact same problem, but we are not allowed to use index of. So we're going to have to do this the old-fashioned way. Less power tools. So now when I ask that question, where in our string is the first occurrence of C, we don't have an answer. Because we don't have index of. Correct? We could write our own index of. That might be a pretty good solution to this. But let's say we're not allowed to do that either. So what we might do, we might create our string answer, start off as the empty string. Then we might want to create a Boolean variable called found. Maybe start this guy off at false. Okay? We'll write our loop that goes through the entire string. I is equal to 0. I is less than s dot length. I plus plus. Then we'll say if s dot char at I is equivalent to C. If I'm looking at the character that I want to remove, and I have not already removed one. That is, and found is equal to false. Or I could also say and not found. Not found and found equal false are identical. I'll do found equal false for right now, for no other reason than it's a little bit easier on the eyes than not found. Although not found is more efficient. This is actually inefficient. If found is false, false equal false is true. I'm actually having to ask an extra question. It's redundant. But this is easier to follow, to say is found equal to false. All right, so if I have found the character that I would like to remove and I have not already removed one, then what am I going to do? I'm going to set found to true and continue. What does continue do? Goes to my next iteration through the loop. Otherwise, I'll set answer equal to answer concatenated with s dot char at I. So the one time that I want to skip it, I'll get inside this if statement and I'll skip it. That's what continue does. It says skip it. All the rest of the times we'll just build up our characters. After the loop, return answer. We should see this guy works the same. Remove first char 2. There's our elephant with the A removed. Make sense? Okay, so a couple different ways to solve the same puzzle. We may have suspected that the index of solution would actually be shorter. I might actually say that this solution is maybe the little bit cleaner one. It's close. Index of, we had to write 2 loops, but we knew exactly where we were going each time. The reality is this one is probably more efficient, the one that uses index of. Why do you think it's more efficient? Why is the first version of remove first char, this guy down here, more efficient performance-wise than this guy up here? Go ahead.
Does the top one have to like go through it more times? Maybe.
No, both of them are going to go through every single character in the string.
Yes. I don't really know that.
It has to do with the second one where we knew exactly where the first occurrence was. So we just went to everything up to, we went from the beginning of the string up to, but not including that position. Then we went from that position plus 1 up to the end of the string. But the first one, the one we just wrote, the remove first char 2, this guy, he doesn't know where that first occurrence is. He just keeps looking for matches on C.
That's what I said.
And the very first time he marks it as false. They're still both going through the string. They're still both going through every character in the string. But this first one, we're doing something extra each time through the string. We're asking a question. Every single time we go through our string up here, we're asking a question. Am I looking at the character I'm interested in? And have I already found it once? So whether or not we get inside this if statement or not, we are still always, 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 always asking this question up here. And questions take time. Okay, that doesn't make it a worse solution, and in this particular case, the performance is going to be negligible. They're both going to seem like they happen instantly. But this one down here, because we knew right off the bat what this one is. Well, what I just said is true, but in actuality, I would argue that the one that we used index of, as it's currently written, is actually less efficient. So look at that and tell me why you think this one is actually written pretty inefficiently right now. It has to do with how for loops work. A small little change and we can fix it. Go ahead.
Don't like for loops have to like store stuff and then keep going back and stuff and like I don't know. Just thinking about like the stack stuff, but maybe that's wrong.
Well, it's nothing. Stack stuff is unrelated to this.
Oh. I don't know that.
I'm not asking you trivia questions. I'm asking you to review the code and tell me where you think there might be some problems of. This isn't something I'm asking you to come out of the back of your mind with. Look at the code and see where you might see some inefficiencies because of how for loops work. And we're looking at just this bottom one. When we go into a for loop, this part of the for loop happens exactly one time, correct? And only once. When does this happen? Every single time we ask the question, right? Every single time we go through, we say, is I less than S dot index of C? What's this guy? It seems so benign, just sitting there, all one-liney. Boils down to an int, yes. But what is S dot index of?
Instance thing.
It's a method, instance method. How many lines of code do you suppose are in that index method or in that instance method? More than one, probably, right? We could write that method ourselves. Probably be 5 or 6, 7 lines of code, something like that, right? Every single time we come through this loop, we are executing that method again. if we just said int pause is equal to this, and then went to less than pause and pause plus 1, now we're efficient. Before, we were literally calling the index of method every single time we spun back through the loop for this top loop. We lucked out, and in our second loop, we were only calling it the very first time we called the second loop, because this part of the loop only happens once. But the Boolean expression part of our loop happens every single time. The truth could be said that this is also true. We're calling s.length over and over and over and over again. That make sense? So couldn't we store the length somewhere? The reality is this is actually okay because we know how the length method works for strings. By we, I mean it's common knowledge for programmers. Strings inside of objects, and this will make sense to you when we write our own objects next class. Today's class is the lead up to writing our own objects. Strings, they don't calculate their length. As a string is built, it knows its length. So as it's being built, it accumulates its length. So when we ask it for its length, it's not a calculation. It just gives you a number. So it's no more efficient or inefficient than if we just stored the number ourselves. Okay? But I promise you that this index of method is a calculation. It's spinning through that string, looking for a char, because you had to provide it some input. You're saying, hey, find me where the position of this guy is. Okay? So I would not abandon our pattern of using s.length. You could certainly say, int the length equals s.length, and then just use the length from that point forward. But more importantly in this little exercise is that calling the index of method every single time through the loop, unless we were expecting a different result each time through, is inefficient. If potentially the result could change, then we'd want to keep calling it. That's part of the solution to the problem. Okay. Make sense? So we'll go ahead and remove char 2 code. We saw that alternate solution to it. And we'll leave our remove first char. And let's just make sure it still works. Yep. Okay. So now we can remove the first occurrence of a char in a string. We can get the smallest char in a string. And then we have this extra base to decimal crap. Let's get rid of that. Now what? Well, we're back to our static string reorder string. I want to create a brand new string that is the original string in alphabetical order. Well, I'm creating a brand new string, right? What's the first character that should go in that string? Answer is equal to answer concatenated with what? What's the very first character that belongs inside of answer? Smallest string, the smallest character from S.
Yeah.
Okay, and we can get that by calling our return smallest char. So we'll say driver dot return smallest char from S. Okay? So now we know the smallest character. Well, then what do we do?
You remove the smallest char.
And we got to remove it from S. And we need to keep doing that over and over and over and over again until what? Until S runs out of characters.
So can we use a for loop?
We could.
Fine.
A for loop is fine because we do know how many times it has to run. I think a while loop in this case makes at least as much sense. So I'm going to say this. While s dot length is greater than 0, as long as there are still characters in s, what are we going to do? We're going to say answer is equal to answer concatenated with driver dot return smallest char in s. Then we'll say s equals driver dot remove first char from s. Which char? The char that was the smallest char. So we probably want to store smallest char in a variable called sc, let's say. So I'm going to say sc is equal to driver dot remove smallest char. This gets back to what we just talked about with efficiency. So I'll call return smallest char one time, storing the result inside of a variable of type char. Then I'll concatenate on answer sc, and then I'll remove sc from my string. Ultimately, I'll return answer. So reorder string creates a blank, an empty string to build our answer in. We also create a variable for storing our smallest character each time through. As long as s still has some characters in it, what do? Well, we set our smallest character equal to the current smallest character in s. Then we concatenate the character we just found onto our answer. Then we remove the smallest character from s, storing the result back in s. So s should be one character smaller than it was the last time through the loop. We'll keep doing this over and over and over again until s finally becomes the empty string. So there is elephant in alphabetical order. And it did not make a distinction between the capital E and the lowercase e. It just happened to be that the capital E was the one that came first when it removed it. Make sense? Okay.
So
Go ahead.
can you scroll to your return smallest char? One I just want to see. Oh yeah, we left the uppercase thing in there.
Mm-hmm.
Okay. Yeah, I forgot about that. All good.
All right, so we have a working solution. Now this guy will work if we pass in any, just bang on the keys a bunch of times. It'll alphabetize that. All right, so trust me, it's working. This is pretty inefficient in terms of the number of steps we are actually taking to reorder a string. So for a string like elephant, which has 8 characters in it, we are literally building 8 brand new strings. Well, we're building 1 brand new string with our answer. We are building 8 additional strings as we remove stuff from elephant. So 9 strings are created as a result of that, of our code, and only 1 of them is kept. So it's kind of like deciding what color paint you want to have on your house. So you build 9 houses, paint each one a different color, then destroy 8 of them. Definitely the way to do it. It's great for the pocketbook, right? Okay, so that's a weakness of strings, is that they're read-only. So if we want to manipulate strings, we have to rebuild We have to build brand new strings. It's a challenge. That's where arrays come in. Okay, so I'm going to kind of briefly introduce arrays. Then we'll take our break. Then we'll come back and really dig into arrays. Okay? And we'll see. If we happen to get through the stuff, we might get out a little early tonight. I wouldn't count on it, but stranger things have happened. But I've been seeing a lot of yawns tonight. Might be one of those nights. All right, so an array is a collection of like values. Well, let's call it like types under a single variable name. So strings are a collection of chars under a single variable name. Arrays are a collection of like types under a single variable name. So we can have an array of chars which would be similar to strings. We could have the array containing at bucket 0 an H, at bucket 1 an E, at bucket 2 an L, at bucket 3 an L, at bucket 4 an O. Okay? All chars. But arrays are primitive types. Ish. Arrays are primitive types-ish. Historically, arrays are primitive types. In modern languages like Java, they're actually implemented inside of objects, but they still act like primitive types, which is actually interesting because strings are implemented in objects but act like primitive types as well. Okay? So, in any case, arrays are collections of like types under a single variable name. They work like strings in terms of indexing and length. So the length of an array, if the length of an array is 5, the legal buckets are 0 to 4. So it's 0 indexed just like strings are. So you don't have to relearn like, okay, which way is the arrays? They're both the same. Okay? Benefit of arrays is that you don't have to hold chars. You can hold a bunch of ints. You can hold a bunch of booleans. You can hold a bunch of chars. You can hold a bunch of doubles. You can hold a bunch of floats. You can hold a bunch of objects. So you can have an array of strings. You can have an array of dog objects, which we'll learn how to write next week. Okay, so you can have an array of anything. Strings, collection of chars. And we've given you some nice methods for working specifically with collections of chars. Arrays are more general purpose. Okay, although up to this point we've used strings pretty general purposely, whatever. All right. Now, the big catch here that we're going to talk about is arrays are implemented using contiguous memory. What does that mean?
Contiguous, sharing common border, touching.
Yep.
Adjacent, neighboring, joining. I've never even heard that word before.
We'll see. Well, I do have a PhD. All right, so let's just make this 6 long. I don't remember when the first time I heard that word. Maybe it might have been when I learned arrays. So if each of these is a bucket of the array, by being contiguous, it means when we put this array in memory, each of these buckets must live exactly next to each other in memory. So, let me copy it this way. If we put memory addresses under these guys, and we're going to get into memory a lot after our break. If this was memory address 100, this might be 101, this might be 102, 103, 104, 105. They literally have to live right next to each other in memory. And this goes back to what we talked about earlier in class when we were talking about how memory is subdivided. And, you could have, each one just holds 32 kilobytes of stuff. Well, this 32 kilobytes of stuff, that's bucket 0 of your array. Let's just say it's an int. 32, not that would be 32 bits, but whatever, just work with me here. So if I had a 32-bit int, right next to that memory would be another 32-bit int. That's part of that array. You don't get to put one int here, another int over here. So what's nice about arrays, and we'll see this, is that they're very, very fast because you can mathematically calculate how to get to an individual bucket in an array. But they're very, very, very memory inefficient. If you need to store a billion things, let's say you need to store a billion integers, you need to have 1 billion times 32 bits of storage space in a row to hold that integer.
But not all computers have that.
Potentially not. So that's where arrays have their limitation, but they're really, 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 really fast. Okay, but they do have that limitation. All right, so let me just take a couple minutes and just show you the quick syntax for creating an array. Because the next step is pretty verbose, so I want to kind of go up to where we need to stop and not. So let's just say I'm going to store an array of integers. So let's say this is going to be the integer 5, the integer 7, 14, 2, 1, and 8. And let's say I name this array AR for array. I would define it using this syntax. Int array AR is equal to a new int array with, what do I have in there, 6 integers. So this syntax would create for me this structure with nothing in it. They'd be blank right now. Then if I wanted to put things in there, I would say things like AR at bucket 0 equals 5, AR at bucket 1 is equal to 7, so on and so forth. That's how you'd actually load values into that array. Bucket 0 is a 5, bucket 1 is a 7. Okay? Similarly, if I wanted to print out whatever is at bucket 1, I could say system.out.println AR at bucket 1.
But at the beginning of all of our things are public static void main, it's a string and then the brackets. So does that
That's an array of strings. This is an array of ints.
So does that mean everything you've been typing is all stuck into an array?
No. Remember when we looked at that, it was the for command line arguments. So if we ran our program from the command line and we typed in A, B, C, and dog at the command line, that array would be filled up with bucket 0 would be the string A, bucket 1 would be the string B, bucket 2 would be the string C, bucket 3 would be the string dog. So that's what got loaded in, not what we typed inside of main. But what's interesting here is I can use the syntax AR at bucket 0. I say this is at bucket 0, so AR square bracket 0 close square bracket. AR at bucket 0 can be on the left-hand side of the assignment operator, so we can write something directly to that bucket. We can also access that bucket to get the value that's in it. So while strings are read-only, arrays are read and write. So now we no longer have to build a brand new array to change one little value. Does that make sense? So what we're going to do after break is we're going to talk a lot about arrays and pointers and memory and stuff like that. And then we're going to go back and we're going to write some of the stuff we've already written today in terms of arrays, sorting and things like that. Kind of make sense? So now, This is a conversation we're going to have often. And I'll even just give you the precursor here in like our last minute or two before break. But the next course, for those of you who are taking it the second 8 weeks, is 537. Yeah, this is 535, it's 537. I think you should be able to register for it now. If it fits your schedule, it's probably not a bad time to take it, just from the perspective of this stuff's already fresh in your mind, rather than taking a semester off and then, so, you know, I realize the stuff is time consuming. It's just the nature of the beast. Stuff that takes me 30 seconds to do now, I spent 10 hours on when I was learning it where you guys are. So that's just the nature of programming, is you start off sucking at it and then eventually it just sort of clicks. But in that class, we pick up where we leave off in this class. Literally, we just keep going. Same slide set and everything. But we talk about things called data structures in there. And the first data structure we talk about is this thing called a linked list. And the linked list is the yin and the yang to the array. So arrays are very fast, but memory inefficient. Linked lists are very memory efficient, but not so fast. Okay, so these things are all linked to each other, which kind of goes back to something that Dr. Locklear discusses a lot. That's the grand ideas of computer science. There's all these things that we think are dissimilar, but they're actually all connected in a weird way. Things from this class connect to your networking class, connect to your database class, connect all these other things. So, you know, it is what it is, I guess. But anyways, a good perk of arrays is that they are read and write. A bad perk about arrays is they don't have a lot of built-in abilities like strings do, because I can store all sorts of different stuff in them. Because they're generic structures, they don't come with a bunch of built-in magic tricks for doing stuff like strings do. Strings are specifically built for holding collections of chars, therefore they can provide for us all this specialty stuff that they think we might need.
You basically sound like how you were describing like Windows is for everything in general, and then Mac is so specific that it has all that stuff.
Oh, iOS versus Android.
You sounded just the same as when you were describing
Yeah.
that.
Yeah, iOS versus Android. All right, make sense? All right, so let's take 20. 15. Do we need 20 or we need 15? You guys, I'm indifferent. 15 minutes it is. There's a chance there we might get out 5 minutes earlier. So, all right, so take 15 minutes. We'll come back at 8:15 and we'll keep going. I got to get